So we've seen some usage of APL. I'm sure you noticed those strange symbols that we use. And it can be daunted at first. There's so many of them. How do you type them all? So for that, we've got something called mnemonics. Sure, the capital M is silent. It's just a fancy word which means a way to not forget stuff. And so there's lots of stuff. If you try to just dive into APL, then you'll probably see a keyboard layout and a list of all the built-in primitives, we call them. And it's just one big jumble of symbols all over the place. And you might even wonder, how do I type those? Never mind, how do I even remember which ones to type? So just briefly, for typing them, there are various ways to do it. The most common ways are to hold down some sort of shifting key and then click some other key. And also clicking a prefix key and then clicking the main key. But common for them is that you need to know what's that other key you need to press in order to get the symbol that you want. There's this mapping between the keys on your keyboard that normally produce letters and numbers and some symbols, and then the APL symbols. And then, of course, you need to know what they do as well. So if you want to know more about ways to type in these shifting keys and prefix, so on, and even alternative ways to enter them, have a look at APL Wiki. We're just going to focus on where on the keyboard do you find them and what do they mean. So here's an example. On the S key, you find this symbol that we call the Upstile. And Richard spoke about monadic and dyadic usage. That's usage with one argument, which is always on the right, and usage with two arguments, which is one on the left and one on the right. So most of these symbols have two meanings, monadic and dyadic, one and two argument meanings. And so too for this one. The trick is, of course, to remember which symbol does what and how to type it. And so the way to remember this Upstile is on S is because it's ceiling. So think of a house, you've got a wall there, and you've got a piece of the ceiling that's going up. You're going to look up at the ceiling. And of course, you're going to say, yeah, ceiling is spelled with a C, even though it's pronounced like an S. So why isn't it on C? That's because C is for cap. You know, this kind of cap, this kind of cap. And this symbol, just like in regular mathematics, is for sets. It means intersection. We obviously can't spell cap with an S, but we can spell ceiling with an S, and then it'll work. Okay, let's have a closer look exactly. So we have the wall and we have the ceiling, and that means in the monadic meaning, rounding up to an integer. Let's say we have a number that's not an integer, and we're going up, and we get the next higher integer. And then for the dyadic meaning, with two arguments, now we need another argument on the left. There, we also look up which one is the one on top, which one is the higher one. So that's on the S key, S for ceiling, kind of. Then right next to it, and by analogy, we have the Downstile, which you might then think should be on F for floor, even though the F key, unfortunately, isn't next to the S key. So that can be. In fact, the F key, we have the actual piece of the floor, an underscore. And while your keyboard probably has underscore somewhere else on it as well, there are historical reasons why we want the underscore there. So let's go back to the Downstile. D for down. Monadic form is exactly the opposite of rounding up. We're rounding down, D for down. And the dyadic form, we go down. We want the lowest of two numbers. And the symbol looks a little bit like an L as well. So L for lowest looks like an L, but it's still down. We're going down. Okay, that's the upstile and the downstile. Notice that these two meanings, while they're not actually the same meaning, they're kind of related concepts. It's the concept of going up, the concept of going down. Up as in ceiling, up as in the maximum, down as in the floor, down as in the minimum. And this way of pairing up monadic and dyadic meanings is very common. It is one of just a few ways that we pair up monadic and dyadic functions in APL. But in every case where there's such a pairing, then it falls into one of these categories. First, let's look at a couple of more where we have related concepts. The next concept is the concept of negation. So the tilde symbol, which of course T for tilde, you find it on the T key, or you could use the tilde key if you have such a one on your keyboard. And it's the concept of negating something. Let's say you have some stuff and you want to get rid of it. You probably scribble it out. So you kind of draw a tilde on top of it. In the logical sense, let's say we have some logical bits, some trues and falses. We represent them in APL, as you've seen, as ones and zeros. And the not, logical not, will flip all the ones into zeros and all the zeros into ones. So we call that not. The dyadic form comes from set theory. Let's say we have all these numbers on the left, but not the numbers on the right. So then the result are the numbers that remain. The concept here is common. It's a negation of something. But other than that, they're not really related to each other. Okay, here's one more. This is the Greek letter rho, which is corresponding to the Latin letter R. So it makes the R sound. It's for the concept of shaping, either giving something a shape or finding out what a shape is. Let's look at the dyadic form first. This is a shape. It's 2, 2. It means 2 rows and 2 columns. And this shape reshapes some data. So we've got 4 numbers on the right, and we're giving them the shape of 2 rows and 2 columns. And the result is a matrix, a table. So reshape R for reshape. So it's on the R key, also because row and R correspond to each other. If we only give it one argument, some data on the right, then we find out what shape does it have, or its length in this case. So we call this shape or shape of. So all of these symbols, there's not really a direct relationship between the two meanings that the symbol have, but they're still in related concepts. This is one of the categories, and there are many more primitives in this category, but I can't go through all of them today. Then there's the concept of a default left argument. One of them you know already, because you use this in very basic mathematics. The minus. Minus really means two different things. It can both subtract and it can negate, and it all depends on whether or not there's something on its left. So 3 minus 10, or just minus 7. And as was mentioned earlier, notice the high minus. It's really important when we have these space-separated lists of numbers to not confuse the function of negation or subtraction with something that's an integral part of the number. But if you think about negation, it's really the same thing as just subtracting a number from 0. You start at 0 and you count down. So the relationship between monadic and dyadic minus is that there is a default left argument in the monadic case. It defaults to 0. And there are others such ones. Say division. And so the default left argument for a division symbol is a 1, which means that the monadic division symbol is the reciprocal, 1 over some number. Another one that has a default left argument is the log or natural log. So this is the logarithm, the 10 logarithm of 1,000. That's 3, because 10 to the power of 3 is 1,000. So the logarithm is the opposite or inverse of power or exponentiation. If we try it with just one argument, the logarithm of 1,000, we get some strange result. If we try it with -1, you should recognize this as negative pi. And this might hint at what the default left argument is. It's e. And so this last example, you could derive that from Euler's famous formula. And e is Euler's constant. How do we type this? It's on the 8th key. In all likelihood, you already use the 8th key to type the star or asterisk, which we use for power exponentiation in APL. And so it makes sense also that its inverse is on that key. Asterisk or star and circle. Why is it the symbol? Well, the star symbol, we use that for power ups, that is exponentiation. And the circle wants to hint at the unit circle, which you might have seen in trigonometry. From this one, we derive things like sines and cosines, phases, and also if we can use this to represent the complex plane. And with the complex numbers, we come into these things about Euler's formula. So the circle function in APL, it provides access to all of these functionalities. And the star symbol is the exponentiation. So combining them together and using e as default left argument, both for logarithm and for the power, and makes sense that it would become the logarithm and natural logarithm in the monadic form. Now, we call this often log. Of course, the real name is logarithm, but let's just call it log. And speaking of a log, here's one. Now squint. Yeah, that's a log. Here's another example. This one is for transpose. And if you've done any linear algebra, then you have met the transpose operation. If you haven't, you'll be just fine. Don't worry. Here's a matrix or a table of numbers. And if we transpose it, all that really means is if we draw a line from the top left to the bottom right, then we just mirror it over that diagonal. And you can see how the symbol represents that mirroring axis. Okay, but we're going to talk about the default left argument here. Let's extend our example to 3 dimensions. So this is a 3-dimensional array or a rank 3 array. If you don't see it, I understand. Think of it as 2 layers that are stacked on top of each other. Now we can see that there are 3 axes we can move along. There's the first axis, which are along the layers, first layer, second layer. The second axis along the rows in each layer. And the third axis, which is along the columns or the individual elements in each row. So if we make a flat representation of this, so it's easier to type on a computer, it will look like this. And what transpose then does is it allows you to reorder the x's. So here we reverse the order of the x's. The middle x's stayed the same. That's the enumeration of the rows, but we flipped the ordering of layers with the ordering of columns. And that is what monadic transpose does. It just flips backwards the order of the x's. So the default left argument isn't a constant like we had with logarithm, where it was e, and with negation, where it was 0. It depends on the argument you're giving it, but it's still predictable. And so if we apply this on just a normal table or matrix, we just flip the order of the axis. We also have some related symbols. For example, there's this one. By now, you should be able to guess what it does, because the transpose was flipping over its line, and so this one flips over its line. We call that reverse because, well, it reverses stuff. And then there is its sibling with the line horizontally, which means we flip over the horizontal line. I like to call that one flip. Okay, that's a whole lot of new symbols, and how are we going to type them? So let's bring back the keyboard and have a look at the number row. Can you spot which one is the odd one out? It's 0, because it's not in its right position. It should really be to the left of 1. So let's get rid of it. Okay, now we got the numbers from 1 through 9, and 5 is right in the middle. It bisects the number row, the part of it that's in order, into 2 equal halves. That means we can rotate around the 5 like this. And that would be a good place to have the symbol that mirrors, that reverses. And then that has the vertical bar. If we go slightly to the side, we get the same thing, just a bit askew. And if we keep going, it falls all the way on its side. So that's where you find those 3 related symbols. Okay, let's go back to the middle. Notice that there is another symbol there. In fact, we sometimes have the shift key which lets you choose between the 2 APL symbols on the same key. In this case, is actually the equal sign, which is the regular symbol, and the shifted one, which gives us the reverse symbol. Why is equal right there on 5? Well, it divides the number row into 2 equal halves. So that's pretty easy to remember. 5 is in the middle. If we go slightly out to the sides, then we get a little bit less than 5. That would be less than or equal to when you do plus minus 1, and greater than or equal to. And if we keep going out further, then you go less, you get less than, and you go more, you get greater than. If you keep going left, then you end up all the way down in the negative numbers. So that's where you find that negative symbol that we had before. And if you keep going up, you're so far away from 5, it might as well be different from. So these are just some examples of APL primitives that have default left arguments. And that's the second category of pairings of monadic and dyadic forms. The last category are the ones where there's really not much of a relationship between the monadic and dyadic forms at all, but the symbol in question is a really nice one for both of them. And here are some examples of that. The up arrow and the down arrow. Let's do these one by one. Let's start off with drop. Drop is dyadic down arrow. We have some data on the right and a number of elements on the left that we want to drop. An arrow down is a good symbol for dropping things, right? So we drop the first 2 and we have the remaining 3. By analogy then, if down arrow is a good symbol for dropping things, then up arrow would be a good symbol for taking things. So to take on the same data, and we get those elements that we dropped before. We're taking those. And we find these on the Y key and the U key. Why is that? Well, think of a synonym for taking. Take, pull, yank. We're yanking elements. So Y for yank. And dropping, well, where do they go when you drop them? Well, we're sending them to the underworld. So U for underworld, yank and underworld. Okay, what about the monadic forms of them? They're a little bit more involved. The monadic up arrow we call mix. Here we have a list of two lists. And mixing makes them into a matrix. What happened? We had an outer axis. The rank is 1 in this array. The overall array is just a list. But each element itself has its own axis. So we have inner arrays with their shape, their dimensionality, and the outer array with its shape and dimensionality. And mixes those shapes together so that we get a single array that has, instead of 1 dimension, 2 dimensions. And then by analogy, split can take a matrix and we take the 2 dimensions that it has and split them up. What happened? These were the number of rows and these were the number of columns. So we have 2 dimensions in this array and we split them so that we just have a single outer array with a single axis and inner arrays with a single axis. And finally, we have the Greek letter epsilon. Actually, it's called a lunate epsilon, which you might have seen in mathematics, where it is used in sets to say that something is a member of a set. And that's pretty much how we use it in APL as well. But first, the monadic form, enlist, is the Greek letter E, so it fits with E in enlist. What does it mean, enlist? Make something into a list. Here is our list of lists, or vector of vectors from before. And enlist joins all the elements into a single simple list. That's enlist for you. And what's about element? E for element, or element of. We have a set of things on the left and a set of things on the right. We're asking which ones on the left are elements of the collection on the right. And then we get a Boolean result back that says that, yes, there's a 1, there's a 2, there's a 3, but there's no 4 and there's no 5. So E for enlist, E for element, E is the key you find it on. That should be easy to remember. E is the Greek epsilon. The 2 letters are both visually and historically the same. And so this is the last category. And in fact, all APL functions that are built in with a language are in one of these categories. Brian is mentioning also that another way to think about the up arrow and down arrow as mix and split is that mix increases the rank, increases the number of dimensions. It takes some inner dimensions and adds them to the outer shape. And so it increases the rank. And so the up arrow means an increase, and down arrow takes a dimension from the argument and hides it away in inner elements, and therefore the rank drops, which is another way to remember that. And so these are the ones we went through here. There are many more in each category. But if we split them up in their individual meanings, then these are the ones that we went through today, both the meanings of them and how you type them. And I'd say that for 25 minutes, learning all of these, that's pretty good. We have mnemonics for pretty much all the symbols, and you can find those on APL Wiki. Now's the time for you to ask any questions. I've got a question here. Quad seems to be used a lot. Quad is a wide, elongated, vertical square. And the question is, what is that function? It's not really a function. Instead, quad, it kind of looks like a box. And the mnemonic for that is the way sometimes you hear people speak about their computer as their box. And it's a really stylized image of the computer you're at. Look at it as a screen or as the main body of the computer. And so we use that for things that have to do with the system itself, not the core language. The quad on its own is used for input and output, and quad with some names of a system functionality after it is used for additional things that are not part of the core language. It could be for additional types of input and output to, say, files. It could be for handling various data types or getting meta information about the language. Is quad explained in APL Wiki? Quad itself is explained. If you just search for that on the APL Wiki, you should be able to find it. Also, a small amount of further quad functionalities are explained there. Otherwise, look in the documentation. If you have an installed APL system, then you can type quad and it will suggest names, and you can click on those and get those auto completed. And after that, you can press the F1 key and go to the documentation for them. Otherwise, you can go to help.dyalog.com and you can find system functions there, and you'll have a whole list of system functions as well. You'll have links to all these things from the APL Wiki as well. There's also a link to the documentation suite. In general, APL Wiki is your answer to everything.